So effectively, we're creating fake data, or as I call it, data science in reverse. So normal data science, obviously you start with data, you get to insights. Here, we're going to start with insights, move to data. So why do it in the first place? Project that I did started about 3 years ago. We're looking, obviously, Synapse back then, just SQL Data Warehouse, was in its infancy. And we were trying to determine, back when I worked in a consultancy, effectively, at what point are we talking data size wise? Is it better to use SQL Server or Azure SQL database, or to go make the cost commitment to change to SQL Data Warehouse / Synapse? Therefore, we really were looking at benchmarking cloud MPPs. And with the way MPPs work, and that's an entirely different talk, but one of the big things that we have to know is that data distribution matters due to the fact that data is distributed among multiple nodes, that in order to get a true benchmark, you really do need real world distribution of your data. The other nice thing about that we wanted to do was to be able to dial a size. So obviously, as we're benchmarking, we're looking at what is a 10 gigabyte data set look like? What does a 100 gigabyte data set look like as far as being able to benchmark performance between the two? The next thing, some real world geography and variability, right? Because I'm sure any of you guys in consulting as well love to do demonstrations to potential clients. My favorite thing in the world was to do that. And obviously, when you're doing so, having some sort of a demonstration data set, very important, but obviously you can't use even differently crafted, shall we say, data sets from current clients you have. The availability, especially back then, of any really purpose-built fake data sets was limited. So for instance, when you started up an Azure SQL Data Warehouse instance, you had the ability to use the AdventureWorks DW data with a massive 70,000 record fact table. Ooh. So not really a great demonstration of the capabilities of something like Azure SQL Data Warehouse, especially for the spend that you're asking someone to make on it. And then just lastly, it was a fun challenge. I always like to stretch myself, see what I can do. It's something, obviously, I think all of us in this line of business need to do, because everything is changing so quickly that it's just good to extend what you can do. Much of the code base, however, we figured out can really can be used to pseudonymize data. And we'll get into exact definitions of that later, but it's the type of pseudonymization that's more human readable. So you're not giving hashes for things, you're giving fake people, for instance. You're creating necessary statistical noise sometimes to be able to make sure that that data isn't attributable back to a data subject. And that's typically can be used very well for like test and demo data sets for the organization. So this is actually me. And this is really cool. I would suggest you look at it if you're interested. So this is an actual website called This Person Does Not Exist. This is an AI generated picture of a person. So they've got several you can go through. It's just really interesting that not only now evidently can we generate data about fake people, we can, in theory, generate actual fake people pictures. So the real me. So my name is Britton Gray. I'm the Director of Business Intelligence at a nonprofit called Project Lead the Way in Indianapolis, Indiana. We create and help administrate curriculum in engineering, biomedical science, and computer science for mostly secondary education students. That said, we do get into the elementary space as well with general science courses. Our courses are designed to be very interactive, very hands-on, teach not just the science itself, but things like ethics within there. So our mission is to really prepare kids for what a STEM career would look like. So I have an MCSE in data management analytics from what Microsoft has told me. That will cease to exist next year, but I can still claim it for now. I'm a member as well of the International Association of Privacy Professionals, working toward my certification in European data privacy. That is a long process. It's several hours of training plus about a 400-page book. The reason I do that is as director of BI in a relatively small organization, I am also effectively kind of a secondary data privacy officer, the one to really determine exactly how technically we implement data privacy initiatives because we keep data on kids. That's extremely important. So that's part of my job, and one of my passions as well is to make sure that data privacy is kept at our organization. My Twitter, I Dream in SQL. I don't know if you guys have. I actually have. It is a really weird experience. And then I've got a couple projects on GitHub, including the one that we'll be going through, and I'll have even the Finland specific stuff. So that'll be available for you guys to get. Absolutely make it publicly available for not just use, but please feel free to improve it. We're a community. This is my claim to fame, Finland-wise. Got to go see Ismo Leikola actually, I think earlier this year, and Vesa told me to make sure to tell you no ni. So hopefully I did not just murder your language. Okay, so we're going to talk about using real world data as really a seed to create fake data. That's one of your best options. We're going to talk about what I call believable inconsistency. So effectively just making things so there is still a real portion of inconsistency, that it's not just straight randomness that's very obviously straight randomness. Considerations when using this sort of a thing for masking, and then talking about the original project that I created, where we created a fake business, generated effectively a star schema for that. So we use real world data when possible to create a fake data set because as there is a saying, every good lie contains an element of truth. So if you want to make it believable, start with the truth, work backwards, so to speak. So these are the main data sources that we used, at least here in the US version. We have our government is several different agencies that sometimes talk to each other, sometimes don't. So our data is very spread out as far as being able to get it. So one of the main things, anything involving people or places, typically is going to be our Census Bureau. And then the Census Bureau has some socioeconomic data, but our IRS, which is effectively our tax agency, does also keep good data on incomes and whatnot, and especially the stratification of those incomes. Economic data comes from our Federal Reserve Bank, a specific branch of that. They keep a great resource called FRED. It's great time series data as well. So for instance, as we'll get to in a little bit later, it's time series of, for instance, retail clothing sales. So it can get very specific there. It's great data. It's been kept in some cases as far back as about 50 years. So, great resource there. Climate data, climactic, would be for us our National Weather Service. Effectively, for every single weather station we have, it'll tell you, our monthly averages and such. And when you're doing, and again, we'll talk about when you're doing clothing sales, that's important stuff. For you guys, Statistics Finland seems to be a pretty good source of just about everything. There is a specific service within Statistics Finland here, Paavo, I believe. So that's at a postal code level, but there's tons of statistical data sets really at a country level, region level, those things. So it was a great resource. I enjoyed using it to get the Finnish data. There are name files too, which our Census Bureau has name files, and that's actually in a slightly different place, and that's right there. And this again, just Statistics Finland, but give a little bit of variation there. And then the Finnish Meteorological Institute, I saw effectively has downloads of climate averages for different areas within Finland as well. Another big important thing is just general geospatial. So you give people places to live, for instance, or places to be. You're going to want geocoded data. So in the US, the Census Bureau offers, as I talked about, a GIS database called Tiger. So it's effectively in, if you guys are familiar, Esri shape files. So those can be programmatically parsed. I have a SQL Server extract available. I'd say it's on my GitHub, but there's technically a link to a Dropbox on my GitHub because it's a very large extract, and therefore GitHub did not want to directly host that. So that is at block level information. So one block of one street, effectively, what we call a census tract. And that's geocoded. So you can say, for instance, from 100 North Main Street to 199 North Main Street, odd addresses. Here's your latitude, longitude. So that's extremely helpful when trying to create fake geocoded data. In Finland, one of the best sources that I found for geocoded address data is the Open Address Project. That is worldwide. Technically, that said, there are a lot of places that are still missing, that are coming into being. It's obviously a crowdsourced type event, so there's stuff being added all the time. I looked, the Finnish data appears to be mostly complete, if not completely complete. That said, if we look, Sweden, for instance, other than looks like some little areas of Stockholm and a couple other cities, is missing. Norway supposedly is completely there. as is Estonia. So there's good stuff for a lot of countries. There's still some stuff that's being developed for others. In addition, and I evidently was a victim of autocorrect there, the Finnish Postal Service has a complete block level download as well that you can pull. So effectively that same type of data that I was talking about in Tiger. The only difference is that's not geocoded. So it might be a really good source to say cross-reference this data against to see if everything's there. But that's also a pretty good source of at least address data. So believable inconsistency, as I call it, don't be randomly boring. If I just put a random number generator on something and I say, pick this from a list, pick this from a list, you're going to see just a flat, straight, boring distribution of your data when you try to do any sort of amalgamation or addition of that data. So and this may be a translation thing. There's something in statistics that we call the central limit theorem. And effectively, that states as you get more data points with a certain mean and standard deviation, the more data points you add to that, the closer you revert to that mean as a whole. That's the enemy in a case like this, because if you're putting tens of millions of data points with a seeded mean standard deviation or something like that, it's going to be very obvious once you put that up to that level that that's exactly what you did. It's a little tough. There are some possible solutions to it. I'll demonstrate a couple of those here in a minute. One is to create what I call layers of randomness. So effectively adding different wavelengths and amplitudes and putting them on top of each other. So if you think back to physics and wave, effectively, putting waves on top of each other, it's the same type of thing. And I'll show you an example of that here. So here I've got what I would call just generally a starting point, and that's 2000. I've got a general trend upward a month of 20 units with a variability of 50 within that. So I could go up by as many as 70, down by as many as 30. Effectively is what we're looking at there. Excuse me. I will add at this point a 12-month and a 36-month variability wave to that as well. I'm going to show you effectively the cumulative effects of those things. And if I do that here, so I'm going to refresh this a few times. And if we notice the blue line here especially, as I refresh, doesn't really change a whole lot. But once you're adding the 2 levels and the 3 levels of variation, you're starting to get a lot more, and something that looks more like something which has a larger trend but noise within it, which is typically looking a lot like more real world data. Now, even in this, you're going to be somewhat of a victim of the central limit theorem. So this is visualization really shows that, where we're tracking effectively the variation divided by the time. So the variation from effectively that 20 addition as time goes on. So if we keep doing that, so we'll notice that blue line really doesn't stray much beyond 0, but our orange line, which is our 2 level, and our red line, which is a 3 level, can really start to create variation there, even on a long-term basis. So I'll pause really quickly and ask, are there any questions, comments on that part? Okay. So, sorry. The other thing is we can incorporate some real world data into that randomness. And I'll say that geography can be quite useful there. So effectively starting with a geographical component and moving out. So I'll show an example of that. So here in the state of Indiana, where I live, we have 4 major sports teams. We've got, we'll call it a blue team, a gold team, a green team, and a red team. If I were to just say, hey, I'm going to look at the relative popularity of the teams in different places in Indiana, this is just a straight random extract of that. So everything here is just statistical noise. There's no real insight to this data other than the fact that in the state of Indiana, there are these 4 teams. Now, if I look at where these teams are physically located and really do a distance adjusted randomality of that, I can start to get a little better insight. And of course, Power BI is going to be a little bit slow. There we go. So now I can tell that my blue team seems to be more popular in Indianapolis than here in the northwest part of the state, the gold team right at the north part of the state here, and then toward the southern. So this is, again, where there's still some level of randomness, but that randomness seems to be much more concentrated, or the popularity is more concentrated toward a specific area. And in order to do that, I created, and I would suggest creating in this sort of a context. Too many windows here. There we go. So I created and used this. So we've got zip codes here in the US. It's just our postal codes. A script to create effectively a table, which ends up being this, which will give the distance between one zip and another in kilometers, assuming it's within a certain distance, because as we have, I think, 30 some odd thousand zip codes, that sort of a Cartesian product would be awful, especially when you're talking about calculating distances, which is pretty processor intensive. So there is an element to that, but that sort of a table really, when creating any sort of a geospatial variability, is extremely important to really pre-process, because it's going to make the processing of anything based on that data very effective. And this, by the way, this script right here will also be referenced in the GitHub that we have. So that sort of thing you can download. And even here, by the way, in the process that I have here, I'm not using a straight what's called Haversine distance, which is the exact way that distances are calculated. This is a Haversine approximation, which I've created, and it's typically only off by a few centimeters, as long as you're within like 100 kilometers or so of the 2 data points, and it's much faster to calculate even for that. Let me go back here. Now, when using this sort of a thing to mask data, so effectively using fake data as a pseudonymization method. So getting into the GDPR here, Article 4 effectively defines pseudonymization as the processing of data in a personal manner, such as that it can no longer be attributable to a specific data subject. That's the key here, where effectively we've masked the data or we've created statistical noise or something where, and as at least the Irish DPA has said, that any reasonable person with technical capability isn't going to be able to reattribute it to that. There might be some super smart PhD candidate somewhere who might be able to spend hundreds of hours and say, aha, I can reattribute it, but that's an edge case, and they said they're really not as worried about that, thankfully. It's still in pseudonymization. Of course, the difference between that and real anonymization is that it still may be possible to combine the data with other data to reattribute, but there are controls in place to try to make sure that that can't happen. The other bar would be complete anonymization, but that bar is so high as to almost be insurmountable. So we typically don't even think to that level. But under GDPR, once data is pseudonymized, it's under far fewer restrictions. There are some people who go as far to say it's under no restrictions. That's not really the case. But there's most things you can do with data, at least under GDPR, once it's pseudonymized. So creating pseudonyms, though, consistent with ENISA recommendations, which is the European Cybersecurity Agency, it can make the data a lot less human friendly. So if you look, for instance, at their documentation, they're talking about changing names to numbers or to hash codes. Obviously for test data, for development data sets, demonstration data, while again, we're talking about something that then is perfectly pseudonymized, it's really not human friendly. So this sort of thing we can use in order to really make a good fake data set out of a real data set that is still really human readable. So this is an example of do not do this for pseudonymization. So say I've got some original names, and by the way, Pecorine is an awesome goaltender. So I create some replacement values from a name data set. And I just say, I'm going to replace all Vasas with Petris, all Tikkanens with Niskanen. Well, there's an issue with that, obviously. So for instance, if I said Swedish, I'm sorry about that. I just realized. So in Finnish, or at least in Finland, we've got most common given name and most common family name. And if I just do a replacement, for instance, on those, it's going to be possible probably to reverse engineer those replacements. Because if I know, and I was able to download a data set in Finland that tells me, hey, here's the most common actual surnames in the country. If I've got just direct replacements of that, I can probably reverse engineer and say, hey, this Korhonen actually is very well could be Niemi, and really reverse engineer with enough accuracy the entire database that the whole issue of pseudonymization is pretty much moot. So instead, what we typically want to do is to do a record by record replacement. Now, oddly enough, though, once I do that, it is statistically pretty likely, for instance, for names or even for geographic data, that my most common values will likely be those that already existed. So it's a bit of a paradox there, where it doesn't look as much like on a on an aggregated level that I did anything, because we're still talking about things being most common, especially if we're doing so with some sort of a weighted random picking. But it's pretty much impossible to reverse engineer the technique as far as being able to tell what my original values are. Any questions, comments on that one? Okay. Another thing that we typically do with pseudonymization is creating statistical noise. So we're taking original values, especially in fact data, but sometimes in geospatial as well, to make sure that things still aren't attributable. So for instance, when I order things from Amazon, my wife more than me, a lot of things come from Amazon. So if I were to just take that same fact data set or some good version of it, and even though my name and my address may have been masked, if you know enough about my purchasing behavior, you still might be able to attribute that to me just by knowing what that fact data is. So in order to do that, generally, we look at creating some sort of statistical noise to really mask that part as well. So it effectively just keeps those personal information data points from being attributable to me or any other person, while hopefully keeping the overall data distributions largely intact, again, to create good training data sets, development data sets, demonstration. So those real world insights are still available. For geospatial data, typically what I have done is to pick a new data point either within the same postal code or those immediately adjacent postal codes. And that typically creates enough noise while keeping the general geospatial distribution intact. That said, the slight change will be, I mean, if you think about a blur filter on an image, is it's going to create a little bit of outward distribution change from, say, Helsinki or Jyväskylä or Tampere. So those areas will start to suddenly appear a little bit larger, just typically like a blur filter on an image. There is some special care that's going to be needed if there's a time component to that data. So for instance, if I'm tracking someone's location over a certain amount of time, like one of my clients used to, but for very good reason. They were an automobile company who was checking to make sure that effectively car behavior in certain climates, et cetera, was as expected. It was still anonymized, but again, if you know where someone's driving, it could be pretty easy sometimes to go back to figure out, within a few people who that person might be. So there was some statistical noise generated there just to make sure that that was not the case. The other thing that I'll say with that same postal code or adjacent, that's where it also goes back to that table I was talking about earlier with the pre-populated distances. So you can take that table, create another table with it, and say, for this postal code, here are my immediately adjacent ones. And that's some sort of a data that if you're doing large amounts of replacement on from that geospatial data, that it's really good for speed purposes to already have that pre-populated. For date data, typically the statistical noise If possible, we keep only the year. So for instance, for birth dates and such, we will keep the year, but just randomly generate another date within that year, or just say, I'm going to generate another date, within the year, plus or minus a couple months in order to create even more noise. Again, though, if I just say plus or minus 365 days or 90 days or, those sorts of things, that it could be possible because of that random distribution to start to effectively reverse engineer and figure out what was going on in the first place. For other general fact records, what I try to do, for instance, in the case where I order a lot of stuff from an online retailer, is deleting a variable percentage of records per data subject. And the reason we try to typically delete that variable percentage is so even the volume of activity isn't attributable back to a person. So not just the actual specifics of that activity, but the volume of activity, where I may order a lot more things from that retailer than, say, my neighbor does. So by giving some sort of a variable percentage, giving some sort of a percentage to me, giving some sort of a percentage to my neighbor, and so if they say take off 35% of my behavior and only 10% of my neighbors, then that starts to look a lot more non-attributable, so to speak. Any comments or questions there? Okay. So from our original process, effectively building a fake business. So this is the code that generates the fake data set from scratch. So we're going to talk about the process there. So the choice that I made was a retail business. So when creating a demonstration data set, it's easy to dial the size of such a data set. The nice thing is it's an easily understood data model. So I could go demonstrate a retail data set to just about anybody, and they'd understand effectively what the business was doing. There wasn't any need to explain a business model. It's also pretty simple to model, at least on the sales side, from a star schema perspective. So that's a big plus as well. Now within that retail perspective, decided to go clothing. The reason why is that there is a lot of geographic variance, especially here in the United States, on what people are going to buy based on where they are. So if you think about someone in Miami is going to buy a lot different type of clothing than someone in New York. You're probably not going to see many winter coats and whatnot bought in Miami. And I'll tell you a bit of a funny story there. So I went to college in the northern part of Florida. So we had a lot of students from Miami there, but the northern part of Florida, unlike Miami, it will actually get cold-ish from time to time. And when I say cold, I'm talking like under 10 Celsius. So, to you guys, that's absolutely nothing. And even to us here in Indiana. But me having come from Indiana to go to college in Florida, it would get, say, down below 20 Celsius, and you'd see the students from Miami suddenly breaking out the sweaters and the winter coats. And it was a sight to see, for sure. That was that was pretty funny. Anyway, within clothing as well, there's a socioeconomic variance. So while obviously just about everybody buys clothing, the type of clothing they buy is different as well. So that's sort of a different level of variability I can put in things to create some sort of additional geographic variance, because there is, at least here in the States, a lot of geographic and socioeconomic variations are definitely very covariant, especially as you get down to like parts of a city or rural versus urban and those sorts of things. The other thing is that clothing, as I talked about earlier, is well tracked by economic statistics. There are clothing retail sales data going back 50 years here in the States. So that's really easy to start with that real world variability and go forward from there. So first step we had is to generate the fake people. So effectively starting with, in the States data set, we started with geography and went to names from there. And I'll get to that in a second as to why we did that. But you get names and then you get some basic geography. So you look at those real population statistics. So for instance, Statistics Finland has a data set which will give you really good population statistics by age, by gender, those sorts of things, down to a postal code level. And then family statistics as well, just because different households have different makeups. So for instance, as I'll say here in the States, that people who live in more rural areas are going to tend to actually have larger family units because those people are more likely to be married or partnered and are more likely to have children. So if you see people in really urban areas, those tend to be your younger people who may or may not be partnered, but are typically going to be less likely to have children than, say, people where I live, for instance, in the suburbs, where we're much more likely to be partnered and have children, and then people in our rural areas are even more likely to be in that sort of a situation. So again, those things generate that real world variability that is good for insight. And it's also good if you go back and think about MPPs where, such as Synapse, or at least the Azure SQL DW part of Synapse, where data distribution is an extremely important thing when you're looking at trying to see how things perform. So my original project obviously was US specific. There is a Finland, or will be, I'll get it uploaded here very shortly, a Finland specific version of the name geography code on GitHub that is written in Python. And I'll show you here some of the results. So first I'll show you the US version. So I'm here in Indianapolis. The color of these dots, and by the way, I will also apologize, I am much more of a Tableau person than I am a Power BI person. I know that is probably sacrilege within an MSBI type group. It's just what I grew up with, so to speak, on the visualization side. So it's more comfortable to me. These, excuse me. So the colors here basically go from your red tones to your blue tones as you get in different strata income-wise. So if you'll notice, there is more variation here in especially the good old United States, where people tend to be much more economically segregated, probably than they do tend to be there. So you're going to notice that there are definitely that sort of variation actually exists here. So if I look over to dot, so for instance, here's my completely fake person with one child. People here, well, there we go. As we get more rural, we're going to tend to have more kids here. So I go over a dot. This is effectively a completely fake person. There is no Stanley Mason right here at this address, but it's but if I look, so if I go down here all the way at a street level, and so I've got something on East 51st Street. Yeah, I'm still at East 51st Street. So, and this is actually a lat long geocoded dot. There's no having to send an address back to, say, Bing or whatever the Tableau version of that is. It's just lat long coded for very quick visualization. But as you can tell, at least our Census Bureau data is right on as far exactly what that lat long of that data point is. So on my Finland version, so this is our general distribution of data in Finland. So right now I've got a 10% sample going on here. So I'm guessing that this hopefully is pretty close to an actual population distribution in your country. So if I go and I look, so what I'm gonna do here for VESA, because he specifically asked me to do this, is I'm going to look at my very overrepresented ASLAs, and hopefully I pronounced that correctly. If I didn't, please let me know. So if I look, I've got people in that area. So I'm going to put my 10% sample back on and take that off. So same thing, except I didn't really have time to do anything, you know, from an economic standpoint or a family size standpoint or anything like that with the Finland data, but I've got my different people here. And so my code to generate that, show you what that looks like. It's about 174 lines of Python, and Python is just my preferred language. It's something I've been working in for almost 20 years. So it's definitely my comfortable thing, unlike, you know, with C# maybe to a lot of you folks. So I'm effectively here just loading in my files. So my, what is it? My male file, my female name file, and my family name file. Then using random weighted choices to create a first name and a last name, which, you know, first name being given name, last name being a family name. So effectively just using a weighted choice method within Python to create those. This method will take a gender optionally. So if you give it that, it'll just say, give me a male, give me a female. Otherwise, it's just going to randomly choose one. So the nice thing with being able to specifically ask for a gender in this code is if I actually look at male-female distribution within a specific area, that I have the ability to I have the ability to specifically weight that way. So I'm not sure how much this occurs in Finland, but I know here in the United States that there are, oddly enough, geographical areas, for instance, that skew much more male than others. Typically those that are involved in, say, oil exploring or some areas like that, that typically attract a lot more male workers. You'll actually see some pretty decent skews in a male-female population. The other part is the address generator, and this right now I'm using the Postal Service data to get effectively postal code to name, and then right now using the government data stat to get the number of people by postal code And right now, this is only using the open addresses data. It's not using the Finnish name file, or sorry, the Finnish address file. But as I said earlier, it would be a good exercise for sure to cross-reference them to check for the completeness of that address file. So this effectively this loads the addresses in a postal code because it's a large file. It really is only loading, excuse me, it's really only loading effectively all the ones, all the twos, all the threes at once in order to help save some memory there. So when I actually ask for an address, yeah, when I actually get the address, it first actually makes a call to this other method, which basically says I'm going to load the addresses, but because it keeps a cache, if I'm loading in a postal code order, it only has to reload every time I move from, say, the zeros to the ones to the twos. So that helps there. So here is just where I use all my classes and effectively generate people. I'm creating a 5% sample rate based on population. So for every 100 people in a postal code, I generate 5. So again, please take this code if you're so inclined on GitHub, and see how you can improve it as well. I love a good community effort, so plug away. Any questions or comments on that? Okay. So here in the US version, effectively what we did is I started with a county level because most of our population statistics are available really at the Census Bureau on a county level, and that is to prevent accidental attribution to any specific person. Because when you get down to the number of population statistics we have, they're very worried that you can start really reverse engineering someone's specific information, especially for those postal codes, for instance, that are much more sparsely populated than others. So we've really got to start at the county level here in the States. From that, I start choosing a gender, again, weighted based on the population. Now, ethnicity, I did that specifically because there are last name files that the Census Bureau puts out by ethnicity, and as weird as it sounds, that is just one more level of real world distribution when, say, for instance, testing an MPP. That is actually kind of important when you're talking about a built-in correlation between, say, zip code and last name. We have something called a crosswalk file to put a zip to county, and that's just because, for instance, here in the United States, 40% of our postal codes overlap counties. So say 30% of the postal code I'm in, for instance, actually occurs within 2 counties, where about like 15 to 20% of the people in my postal code are in the county that I'm in, but about 85% are in another county. So that's important to do there in order to keep both county level distribution correct and postal code level distribution correct. We get income groups based on the county, look at first name and last name. First name comes from gender. Last name, again, that's where the ethnicity comes in. And then we effectively just choose an address in a lat long. And because those blocks, the census blocks that are generated, at least in the US, tend to be very similar. They try to make them as similar as possible. based on the number of people, especially in larger areas. So it's a pretty good approximation to just say, give me a block within this zip code, and then I'm going to choose an address within that. Now, every good store needs products. So we're basically using a semi-Cartesian product, what I call, to get its size. So these are the attributes of my items. So age being like whether it's adults or kids, the item type, color, brand. And notice, even though my Cartesian product here would be 3,640 items, I only have 1,800 because not all combinations result in a product. So for instance, sorry for anyone who might want so, but I'm not going to sell you a business suit in yellow. You're out of luck there. Again, that also, though, helps to generate, again, some real world insights on, you're not just going to see everything in every color flat. So that's an important thing too. Next, I have to place stores. So where do we shop? So this one, I've gone through several iterations to try to best place those stores. I have a lot of sympathy now for people who have to decide how to do that. So first, I just tried a weighted clustering, effectively a k-means clustering of population by zip code. Well, you can see, for instance, in some places, this creates some issues. I could have my first ever boat stores, I suppose, for things, but I don't think they'd really be shopped all that well. So there have been several other attempts. My current iteration is effectively using an apportionment method. So similar to the way, for instance, that your parliament districts may be created. So you're taking bits of population, equal size, and effectively putting something there, and then trying to make sure that nothing else occurs in that same. And my apportionment score effectively is for every single person, we're taking the square root of this. And that seemed to be just as a trial and error thing, a pretty good approximation. So this is actually in the state of Ohio, where this is putting stores typically pretty well in places where I would do so, in relative population centers, much more in large urban areas like Columbus and Cincinnati, than say out in a relatively small place with fewer surrounding cities. So when creating fact data from scratch, it's probably one of the hardest things to do because there's a lot of real world variability pieces that go into it, and creating just a straight random data set is going to be very obvious and not make a very good demonstration when you're trying to demo a data set. So effectively, I looked at this as adjustment tables, where your choice of one thing is going to influence your choice of next. Each one gets different weights based on what was here. So for instance, men's clothing, this is the general distribution. It's going to be different for women's clothing. This weight will look different. And when you put multiple layers of that involved, effectively you're getting a lot of variation within any specific purchasing behavior. So that's a good way, again, to put those levels of variation on top of what we're doing in order to make a lot of good non-even or even normal distribution type things when you aggregate those up. So those propensities effectively are handled as tables that adjust base probabilities. So based on, so for instance, someone's location, it's going to influence these parts of the clothing. And there probably should actually be an X here because the gender of the person is going to influence the gender of the clothing bought. For some reason I did not put an X there, but these are the kinds of adjustment tables that actually exist based on that. So, we're looking at 3, 5, let's see, 9, 13, effectively about 18 levels of adjustment in order to make sure to create as much real world variation as possible. And this also, the other thing that just isn't here is the first thing it actually looks at is what those clothing sales were in a real basis for whatever month it is, and effectively just adjusts propensity as a whole based on that. So when we do that, we actually create our purchases table. Right now, it goes through one person at a time. That said, it can be run in parallel as far as processes go. So you can really run through, depending on how many cores you've got, 8 people or 16 people at a time, or such a thing. It goes through a period of 10 years. It spreads its output into 10,000 files. Again, because if you're loading into an MPP, that's really important for a couple reasons. One, it allows you to put your generation process in parallel in the first place. And two, if you're using something like Polybase to import into Synapse, the more files you have, the more parallel those loads can run in, especially as you increase your DWUs. So again, it's reading that economic data, the weather data. So I'm much more likely to buy a coat in, say, September than I am in March or April. So it actually really looks at that weather propensity, not just for that month, but it weights it 3 months down the road, effectively trying to simulate someone who thinks to actually buy ahead, which I don't know if that's the way that clothing is typically purchased there, but there's definitely an element to that here where oddly enough, you'll see swimsuits come on sale here in February, despite the fact that it's still quite often 10 below 0 Celsius here. So it's kind of strange, but that's when a lot of that's bought, because it's bought with the spring summer season in mind. So that sort of thing, where you're also buying coats in the middle of August, where here it could very easily be 30 degrees. So that sort of thing is looked at as well. And so really this process, when I designed it, it really looks at the other reason I really kind of did it as a person at a time is because that's how I think. So, and yeah, it's probably how you guys think too. I'm a person, I'm making purchases, what goes into my decision? So those sorts of things. There's also geographic variance, for instance, in color preferences. So someone who lives, again, in Miami is much less likely to buy black clothing than someone who lives more up north, because you're going to be very uncomfortable if you wear a lot of black down there in our subtropical areas. It also groups purchases. So if you go to the store, you're probably going to buy multiple things rather than making tons of trips to the store for one thing at a time. So it works on that premise as well. And again, that will also be on GitHub here pretty soon. That said, that process as a specific one is a bit piecemeal into a few files. So I will apologize in advance for any of you who pull it. Trying to go through that process. I am working on consolidating those files, and we'll have a better README here out pretty soon on that one. So our general takeaways from this whole thing is obviously creating good fake data is a complex process. So when I started this project, for instance, I thought I was going to do it roughly maybe 40 to 60 hours worth of work to do such a thing. I think I'm well over 300 now. So it's definitely one of those cases of I way underestimated the amount of effort it was going to take to do something of this means to make it at least as good as I would like it to be. And there's always room for improvement, even in that. There are more things I'm like, well, if I had the time, I'd totally do this too. And that just constantly happens, and that's how 40 balloons to 300. Using real world variability helps randomness where possible. So there's nothing like using real world data to help seed your random data to make things both believable and giving things really non-flat levels of distribution. Using those multiple layers of randomness help keep things interesting, where you're talking about weighting based on the previous thing, using those waveforms, those sorts of things. And the fact that a lot of these same techniques can be used to mask existing data if you need so for your test data sets, your demonstration data sets, those sorts of things, or even to potentially, put out to another processor in the GDPR world. Those things can be used for that purpose and still keep it, relatively human readable. And then finally, just again, letting you know that a Finnish person generator is going to be available here in a couple of hours when I get it published onto GitHub, and that is my GitHub as well as my Twitter, iDreamInSQL. So with that, I've come to at least the end of what I am presenting. And again, because I really welcome feedback and questions and like to make this a community effort, please fire away with any questions or comments.